All right, we are in section 6.5 now. We're learning in chapter 6 about applications of integration. And we are learning a lot of interesting applications. We can find areas between curves, we can find volumes, we can find the length of an arc, and now we are in section 6.5 and we're going to talk about the average value of a function. So let's just recall here real quick. Let me bring up the whiteboard. Let's say you have numbers 7, let's see, 8, and hold on, and 6. What would the average be of these three numbers, 7, 8, and 6? That's right, Jonathan. Very good. And how do we get that? We
7
add 7.
plus 8 plus 6, all divided by 3.
That's exactly right, Clea. And so you get 21 divided by 3, which is 7. So finding the average is not a big deal, not a big deal. And we are interested, of course, now in section 6.5 in finding what's called the average value of a function. So they mentioned it's easy to calculate the average of finitely many numbers. And these y values, y1, y2 up to yn, those are values from some function. And if we want to find the average value of the function based on sampling some y values, we can do that. But you see the highlighted question there, how could we compute the average temperature during the day if infinitely many temperature readings are possible? So what if we had a function that models temperature, where we could take basically infinitely many temperature readings? So if we go down here to figure 1, okay, you see there a blue temperature function in figure 1, a blue temperature function. And the temperature function is in degrees Celsius. And let's see, the t-axis goes from 0 to 24. I noticed that. Why would that be?
Is it for the time or the temperature, Professor?
Well, the horizontal axis t is for the time. It's in, but why does it go from 0 to 24?
Because
Jonathan says
yeah.
Claire, so I think Daniel, Jonathan, Claire are saying, hey, there are 24 hours in a day, right?
Yeah.
Okay, so t goes from 0 to 24. And let's see, what's the 6 stand for there? T equals 6. What time would that be? On the t-axis. Good, 6 a.m., that's right. T equals 12 would be noon. T equals 18 would be, what time would T equals 18 equal?
6 p.m.
6 p.m., good, good. All right, good Clay, good Jonathan, good Daniel. Okay, so, well, does this blue temperature function in figure 1 make sense? Does it make sense? Well, let's see. So what happens there? When's the temperature the lowest?
Early morning.
Early morning, 6 a.m. And then, oh, I see the temperature seems to be going up. And it keeps going up till 6 p.m. Temperature's increasing. Why would that be? Right, Jonathan. That's right, Clay. The sun's coming up and the temperature's getting warmer. Well, now after 8 t equals 18, after 6 p.m., the temperature starts to fall again because the sun goes down. So this is a very typical temperature function. And you know, with the instrumentation we have today, basically those instruments could take like an infinite number of temperature readings. How could we find an accurate estimate of the average temperature for that day? Okay, well, let's explore this. Are there any questions so far? All right. Okay, so in general, what we want to do is we want to compute the average value of a function, okay, where x goes from a to b, and we're going to take the interval from a to b and divide it into n equal subintervals. So this is like section 5.9, numerical integration. You would have an interval from a to b, and you would divide that interval up into subintervals. And each subinterval would have length delta x. Delta x is equal to b minus a divided by n. Okay, now what we can do is we can choose points in the intervals and obtain an average of the numbers. So if we pick a number of subintervals, we can take a data point, a time, I guess it will be a time point if we're talking temperature, and then a measurement for each temperature. And we would get what you see, we would get what you see here. Yeah, a question, Clea?
No, I'm just saying, is this similar to like the midpoint we used, like we did in 5.9?
Well, the dividing the interval up into subintervals is similar, but then it gets different then,
Okay.
because we're not gonna need to approximate the average value of a function, or like, you know, if it's a temperature function where we have an infinite number of readings, we're not gonna need to approximate that. We can actually find the true average value. Because look at what we do here. Look at what we do. We're gonna take this you say it the right way. We're gonna take this average and we're gonna replace the n with b minus a over delta x. Okay, so let me show you what they're. Let me show you that here. Hold on. So okay, so delta x is equal to b minus a divided by n. So this means n, well, what I can do, right, is I can multiply both sides of this equation by n. The n's simplify out, and I'm left with n times delta x equals b minus a. So that means then that, you know, n times delta x is b minus a, and I can divide both sides of that equation by delta x. And then the delta x's simplify out, and then I'm left with n equals b minus a over delta x. That's what we're left with. Well, what I mean is I can write the n, the number of subintervals, as b minus a divided by delta x. And so, for instance, in section 6.5, when they have, and I wanna use the right terminology here. Yeah, when they have in section 6.5, you know, x1 star, sorry, f of x, the function evaluated at x sub 1 plus the function evaluated at x sub 2 plus the function evaluated at x sub n. Okay, and these are just values in each subinterval, and we divide that by n. Well, that's equal to then what you're going to see here. It's a plus here, right? You can replace the n with b minus a divided by delta x. See that? And that's what they're doing. That's what they're doing in the book. So are there any questions on that before I return to the book? Okay, let's get back to the book here. Okay, so they're taking the average value of the function and they're replacing the n with b minus a over delta x. But then you could write that by multiplying by delta x in the numerator and denominator. You're going to get then 1 over b minus a. The average value of the function is 1 over b minus a times the summation of every function value times its times delta x. And so you end up getting a summation. You get a summation for the average value. You get this summation. Okay. So like they mentioned, like for an average temperature function, you could be taking temperature readings every minute, okay, throughout the day. So if you were to take temp like that n there in that summation formula, since there's 24 hours in a day and 60 minutes in an hour, the n would be 1,440. But the thing is, that's how many no, hold on. Yeah, that's how many minutes, 60 minutes in an hour, 24 hours in a day. That's 1,440 minutes in a day. So n would be 1,440. But you see, we can let n get more. We could take temperature readings every second, and then every half second. We could let n increase. If we do that, what's for the average value of the function? What's the average value going to become? What's that summation, that Riemann sum, going to become as n goes to infinity? What would it become? What do summations become as we take more and more subintervals, as we let n goes to infinity? Okay, Yonatan, more exact, and exact means what?
Maybe can you rephrase the question so we can understand it better?
Well, so you see there, here's what I'm trying to say. Hold on. Here's where we're at here. Hold on. So you have okay, you have this. The average value of a function. Okay, and if we take the limit as n goes to infinity, the 1 over b minus a will factor out from the limit. Okay. What I'm asking is, what does this become? What does the limit as n approaches infinity of that Riemann sum become in calculus? You've seen it many, many times.
Infinity?
Well, not n will approach infinity, but what's the Riemann sum become? That's right, Yonatan, an integral, right? It becomes an integral. So You'll get the integral from A to B. And I appreciate all responses. Now we have a formula to find the average value of a function. So that's what I was looking for. I was hoping somebody would say the Riemann sum becomes an integral as n goes to infinity, as we take the limit. But that's what I meant. Are there any questions on that? Okay, give me a thumbs up if you're feeling good so far with this.
Professor, what's the last thing you wrote right here in the last line?
This is AVE stands for average. AVE,
Okay.
that's abbreviation for average.
Okay, thank you.
No problem. So now we can get the exact average temperature. For instance, if the function is our temperature function and it's taking readings every billionth of a second or something, we can get the exact average temperature for the day using a model. And how do these forecasters come up with how many have noticed in the news they'll say the average temperature today is, maybe you look at the news in the morning, they say the average temperature today is going to be 70 degrees Fahrenheit. How many have noticed that? Maybe in the morning news, that kind of thing. Okay, Clay has noticed it. Okay, and IB, and so what they're doing is they're using a model, like you saw in the book there, to model the temperature for the day, and that model is going to differ based on conditions, or based on atmospheric conditions. It's just amazing how accurate they can be now with weather compared to when I was a kid. Now they're like, if they say a storm's coming or rain, we're going to have rain, later this afternoon, they're usually pretty good with that. It's kind of amazing, really. But yeah. So let me see here. So now we define we've discovered that the average value of the function equals 1 divided by b minus a times the integral from a to b f of x dx. And you notice there in the figure 1 where we have the temperature function, okay, you notice how they draw a red line, a red horizontal line that says temperature average. That just means, that's just sort of gives you, I mean, you can sometimes sort of visually see what a reasonable answer for the temperature would be. That red line is a balance point for all the points on that blue graph, that red horizontal average temperature line. It's like the balance point between all those function values on the blue temperature function. So let's go ahead and look at an example here. Let's bring up an example. Okay, let me give you a moment to copy this example down. Okay, and then we'll go over it. Okay, so let's see here. We have a function 1 plus x squared, and we want to find the average value of this function over the interval from -1 to 2. So what I'd like to do, I'd like to draw a picture of this function and over the interval from x equals -1 to 2, and just get a feel for what the function looks like, and perhaps an idea on what a reasonable answer would be for the average. So let's go to Desmos here. I'm going to go to Desmos. I'll bring it up in a moment here, and I'm going to graph that function over that interval there. So you do it too. Okay, let me bring it up here. Okay. So, of course, I want to restrict what x is. X goes from -1 to 2. So let me try to adjust this picture a little bit. Let's see, maybe what I'll do is go to the wrench here, and the x-axis, I'll go from -1 to 2, and the y-axis, maybe I'll go from like 0 to, one moment here, let's see, maybe 5. Okay, pretty good picture. So when x equals 2, y equals 5, because 1 plus 2 squared equals 5. So I mean, all the y values are in other words, this is a complete graph. Visually, it's a complete graph, and you can see here, like if I put my the point here, I'd like it to sort of stay. I wonder. Usually it stays. You know what I mean? All right, well, anyway, there's the point 1, 2. And so when, x is less than 1, all the y values are below 2, right? So if you look at this part, hold on here. If you go through all these coordinates here, all these coordinates, the y coordinates are less than 2. And then when you go x greater than 1 and look at the coordinates there, all those y coordinates for those points have y values greater than 2. Okay, and you can see the functions starting to increase fairly quickly when y is greater than 2. Or when x is greater than 1. So, I mean, if you had to make a guess, what do you think the average might be for this? Let me see. Let me try something here. Hold on. I'm going to put in y equals 1. Is y equals 1 the average value of this function?
No.
Definitely not. Okay. All right. Let's see. Hold on. Well, let's put a few more here. Yonatan's thinking too. Um, let's try, we'll put y equals 2, and we'll put y equals 3. Okay, so if you had to choose between the average value of the function being 1, 2, or 3, what might be your choice?
3.
Okay, who thinks maybe 3? And people are going to think differently. Okay, Susanna thinks 3. Clea thinks 3. Victoria thinks 2. Okay, so we have some different thought processes here, different thinking. IB, question?
What was the question again?
Which like if you look at those like horizontal lines, one of them is at like y equals sorry, let me see. Yeah, one of them's at y equals 1, one of them's at y equals 2, and one of them's at y equals 3. So I'm wondering, in terms of like the balance of the graph, the average, what's the best choice for the average? Y equals 1, y equals 2, or y equals 3? We pretty much ruled out y equals 1, right? Because all the y values are greater than 1. So the average have to be greater than 1. But would it be y equals 2 or y equals 3? And you can see what's happening here. The points here, they're increasing rapidly. So that means those points where the graph's increasing rapidly have to have an influence on the average. They have to have an influence on the average. Jimmy IB thinks it might be 3. Okay, well I'll tell you what. Let's see. Let's go ahead and see here. So I'm going to go back into the problem here. Okay, let's look at the solution. Okay, so there's some stuff here you don't need to really, worry about. I mean, you don't need to worry about this. You've copied the example down. Let's focus here on the solution. So A equals -1, right? A equals -1, and B equals 2. And the average value of the function, right? So in terms of a formula, let's remember the average value of a function is the integral from a to b of f of x dx. So now I'm applying that formula. Okay. And it's just a simple calculus 1 problem, really. You don't need a substitution on this one. You just evaluate the antiderivative. Antiderivative of 1 plus x squared is x plus x cubed over 3. And then you substitute in the 2 and the -1. And it turns out the average value is going to be 2. Take a moment to copy it all down. Let me know if you have any questions, and we'll go back to the picture. I can maybe intuitively show you why it's 2 instead of 3.
So, Professor, I see why is it two, because like I can see the calculation, but like does when we look at the graph, isn't like the graph like the arms of the parabola like going up and up and up? So I always thought it was three.
Well, I'm gonna justify to you why it. I understand, and you're not alone, Claire. You're not alone. I'm gonna show you why it has to be two. It's a good question, and not a problem. We'll answer it. You'll feel good in a moment. Don't worry. Okay, so the one moment here. I drew a little picture here. This here, this is just, I mean, we saw the graph in Desmos, so this here, the graph isn't really necessary, but these are just if you did it on TI 8384 calculator, a good X window would be -1 to 2 with a scale of 1, and a good Y window might be -5 to 5 with a scale of 1. Let's see, where did Mandy says, where did I get the 1/2? This here, hold on here, this part here, well, hold on. So that's B, and -1 is A. The average value of the function is 1 over B minus A, which is, you know, what you have here, times the integral from A to B of f of x dx. All right, Mandy? Is that okay? Good, excellent, excellent. All right, are there any other questions here? So I appreciate all the answers students gave. It turns out Victoria was right on hers. All right, I'm just making that a little more. Okay, so let's go back then to Desmos and take a look at this. Okay, so actually your intuition was right for those of you that, I mean, in a sense, what I got the idea was the function's really increasing, right? It really increases here. It's starting to really increase. So the points are growing and growing and growing. The y values are growing, and what's happening is relative to these other y values here, which are growing kind of slowly, you have some y values here when you get uh, you know, close to x equals 1.5 that are growing quite rapidly. And so it's kind of that idea where you know, the average, if you have like values, a bunch of values that are similar, and then you have a few big values, it can skew the average. So like for instance, baseball salaries, you might have a lot of players that make maybe around, you know, $300,000 or something a year, but then you have those few that make maybe 10 million a year. And if you take the average baseball salary, it's skewed, it's inflated because of the big values. How many have heard of that kind of thing? That big values can inflate the average. That's something very common in statistics. Well, what's happening here is that the fact that the average is 2, you notice that the majority of points, the majority of y values fall below 2 on this graph, and less of the y values are greater than 2. Okay, so the majority of y values fall below 2, and less of the y values, certainly less of them, fall above 2 or are above 2. But the fact that the y values above 2 grows quickly means that affects the average. And so it balances out to y equals 2. Y equals 3 is just a little too high for the average. The average doesn't get skewed to the right. It doesn't get pulled to the right as far as that. But at any rate, how many found this? Was this helpful? The graphical, sort of a graphical. So let me see here. Let me just take this off here. Hold on. Let me take this off. Let me take this off. Okay. Hold on here. One moment. Take this off. How many found this graphical representation helpful? Masume likes it. Okay, good. So, average value of a function has a lot of applications. For instance, like I had mentioned, if you want the average temperature for the day, if you have a function that models temperature throughout the day, and there are a lot of models based on what kind of day it's going to be, you can determine the average temperature. If you wanted to find the average density of a rod, if you have a rod that has variable density in it, and you want the average value, the average density of the rod, that's another example. You could have, even for instance, you could have average velocity of, like, for instance, blood flow in a blood vessel. Okay, there are medical applications too. Or you could have the average velocity of a car, all kinds of applications. So how many think, hey, average value of a function is a pretty cool idea here? How many are like in section 6.5? Okay, John likes it. All right, and maybe, do we have any others that kind of like 6.5? Think that material is interesting. All right, Clea likes it. Well, good. All right, well, are there any questions before I stop the recording? Okay, I will stop the recording. Yeah, Clea, question?
No,
Okay.
Professor, my mic was off.
Okay. All right. I'll stop the recording then.